Good morning, everybody. My name is Lucian Pullen, and today's session is starting a bit earlier because I have other engagement. As there are no students watching at the moment, I'm going to just continue, and as soon as someone joins, I'm going to switch on the either the Teams link if that person wants to, or I will start, or you can communicate via the chat. Okay. Well, today we're doing two different sections. First up is we'll be discussing some linear momentum, and then after that we'll be doing bodies moving around a rigid axis. Okay, rigid bodies. Okay, so let me just, before I just switch that, the mechanics workbook. For the first hour we'll be doing linear momentum, and the second hour we will be doing bodies around a rigid axis. Now this is the prescribed textbook for the course, and I'm going to go back to the workbook now. I just need to check something. Yes, linear momentum and collisions come before rotation of a rigid body about a fixed axis. Okay, so we will be doing some linear momentum and then rotation around a fixed axis. Okay, and at this point it doesn't seem to want to go there. It's 247. Let me just go to the page while I'm here. 247, 8. Okay, there you have it, a collision. It's linear momentum and collision. We'll go to the problems. First let's go to the summary of the chapter. The summaries, guys, are really important. Well, it summarizes, as the name says, everything that was discussed in that chapter. Literally everything that is of importance in that chapter is discussed in the summary. Okay, like here, the definition of linear momentum. It says there, linear momentum of a particle of mass m with moving velocity v is equal to the product of the velocity and the mass. Then the impulse imparted to a particle by the sum of the forces is equal to the time integral of that force. And I know I'm going too fast, but I will be covering it in the workbook also. I just want to go to the problem. Okay, now I think we are ready and set up. Let me just check if there are any viewers yet. None yet. I just want to enlarge this window quickly. If you see me looking this way and that, I am currently haven't switched on my face camera. Let me just do that for a second, but I'm currently looking at two screens. So let me just switch off my face camera. It should be here. Well, it is the work that is important, so not me. Okay, face camera is a bit tilted that way. Okay, so we have there I am, which is not very important. Okay, so let's get to it. Okay, let's go to the workbook. Okay, it says here that we'll be doing from 12.3 and linear momentum to 12.4. Okay, now let's go. This is on linear, this is on momentum. We'll be doing on momentum and Newton's second law. Momentum and Newton's second law. Okay, now Newton originally expressed this second law, which we usually know just as F is equal to ma, in terms of momentum. Okay, now linear momentum. Okay, let me just underline that. Momentum and Newton's second law. Okay, now generally momentum, as that, I'm just going to read what is written here. In 12.2, it says momentum implies a tendency to continue on course, okay, to move in the same direction, and is associated with great mass and speed. Just picture this, okay? I assume you all know the game of rugby, okay? Or let's just take cars, for instance, two cars, a car and a truck. If two cars about the same time crash, the damage would be about similar because each of them have about the same force, they're about the same size, and if they're moving at the same, or that is not a good example. Let's say there is a wall, okay, a wall, and a car crashes through that wall. Okay, now that hole in that wall is going to be, that is another bad example. When I was teaching in high school, we did this experiment on momentum, but it's not going to be applicable here. But let's just say let's define momentum. Let's not try to use examples. Try to think about it. Okay, so linear momentum. Let's define it. Linear momentum is defined as the product of an object's mass multiplied by its velocity. Okay, so linear momentum is the product of an object's mass multiplied by its velocity. Okay, so linear momentum is defined as the product of an object's mass. So linear momentum is defined as the product of an object's mass with its velocity. Now, momentum is a vector. Okay, this symbol is the momentum and it is a vector. This is the mass of the object and this is the velocity or the speed at which that object is moving. So linear momentum is defined as the product of the mass of an object with its velocity. Okay, that is its linear momentum. Okay, so linear momentum is defined as the product of an object's mass with its velocity. Okay, there is something. Okay, there is a slight lag. I'm also watching the same screen that you guys are watching, and there seems to be a slight lag, but it says here there's an error, but let's not get hung up on that. So linear momentum is defined as the mass times the velocity of an object. Okay, so for instance, let's say there is a 5 kilogram child running at a speed of 3 meters per second, and his momentum would be 15 kilograms. Remember, momentum has units of kilograms meters per second. Okay, because mass is in kilograms and then velocity is in meters per second. Okay? So the units of momentum would be in kilogram meters per second. Okay, now here's very important. Let me just move this up. Very important. Momentum is a vector. Momentum is a vector, which we've already said here. Momentum is a vector. But here's the extra added part, that has the same direction as the velocity. So momentum has the same direction as the velocity. So the momentum of an object is the same direction, is in the same direction as that object's velocity. Now momentum can also be written in unit vector notation. Okay, momentum can be written in unit vector notation. This page is just some rehashing some stuff that you should know. In unit vector notation, this is how you write momentum. Rho is equal to m Vx in the I hat direction plus rho is equal to Vy, that's the velocity in the y, in the j hat direction, plus the mass. The mass will stay the same. The momentum, the velocity in the z direction, the k hat direction. That is momentum in unit vector form. Okay, now we will mostly just be using it in one form, in one direction, so it'll just be mv. So we drop the subscript mvx. Okay, now let's get to momentum in Newton's second law. Okay, now Newton originally expressed his theory of momentum, his theory of, well, his second law. I'm saying theory here. Newton originally expressed his second law in terms of momentum. Okay, now I can explain that easily, but I will not be writing it down. Okay, now it says here, the importance of momentum was recognized early in the development of classical physics. Now, you should all be familiar with who Isaac Newton was. He's the father of mechanics, okay? Actually, I think that honor belongs to Galileo because he became the first actual physicist to do things, put Aristotle's notions to the test. But Newton gave the mathematical basis for modern day, or for classical mechanics, okay? And he also developed calculus to help him with his celestial mechanics. Okay, now Newton developed three laws, as you all know. Okay, the first law, which states that a body in motion will continue at a constant velocity or stay at rest until acted on by a net external force. That is Newton's first law, which we're all familiar with. Newton's second law states that if a net external force does indeed act on a body, it will cause that mass, or that body with mass m, to accelerate in the direction of the force. Okay, and Newton's third law then states that for every force there is an equal but opposite reaction. For every action there's an equal but opposite action. Then he also added this universal law of gravitation, which says that the gravitational force between two bodies is equal to the product of their masses over the distance between them squared. Okay, and then you multiply by the gravitational constant. Okay, now Newton actually, like I said earlier, stated the second law of motion in terms of momentum. Okay, now we are all familiar with F is equal to ma, but that is a specialized case of Newton's second law. Okay, now Newton's second law says that the net external force is equal to the change in momentum of a system divided by the time over which it changes. Okay, now originally Newton expressed the second law like this. He said the sum of the forces acting on a body is equal to the change in momentum of that body over the change in time. Okay, or basically the time rate of change of linear momentum is equal to the net force acting on that particle. Okay, here it is. You can also write this in terms of infinitesimals. Okay? Or it says the small rate of change in the momentum over time is equal to the net force acting on that particle. Okay, now we say particle here. Now we know from modern physics that particles, we usually refer to electrons and protons as particles, but in this case a particle just means a body with mass. Okay, now let's continue. Now this statement of Newton's second law includes the special case of F is equal to ma. Now I will show you how that comes about. Now the change in momentum, okay, we know we define momentum is equal to mv. Okay, the change in momentum is just mv, the change in mass times velocity over the change in time. Okay, now we know that mass is constant, so we can take it out, so it's just a change in velocity over the change in time. Now the change in velocity, we know from first term that the change in velocity over the change in time is nothing but the acceleration. And there you have Newton's second law expressed in terms of momentum. Okay, this is how Newton originally expressed his law. Okay, now here's question number 1. Okay, how can a small force impart the same momentum to an object of constant mass as a large force? Okay. It says, how can a small force impart the same momentum? So we want them to have the same momentum, but there is a smaller force. Okay, so we want the same momentum but a smaller force. Now let's check this out. The object has constant mass as a large force. See, it says, well, the question is, how can a small force, so we have let's say we have a small force, okay, they're asking, how can this small force create the same momentum, impart the same momentum to an object whose mass doesn't change as a large force? So basically, how can a small force impart the same momentum to an object of a large force? That is the introduction to impulse. Okay, so we have force is equal to the change in momentum over the change in time. This is question number 1, by the way. Force is equal to the change in momentum over the change in time. Now we want the force, we want the same momentum but we have a smaller force. In this case we have a smaller force, but we want the same momentum, same change in the momentum basically. Okay, if we say, let's say we start the momentum at 0, then this change in momentum will be the same, but we want the same force, the same momentum but a smaller force, so it must act a large force to create that change in momentum for some time period, must act over a time period. But if we have a smaller force, then the smaller force, in order for it to create that same change in momentum, must act over a longer period. Okay, so this is just an introduction to momentum and impulse, and this is basically what we'll be doing most of the problems on. Okay, impulse. Okay, it's basically rewriting the change in momentum. Okay. All it says here that the change in momentum is equal to the impulse. It says impulse is equal to the change in momentum which is equal to the integral from the starting time to the finish or the end time of the force with respect to time. Okay, so it's the integral, it's the impulse of the net force acting on the particle is equal to the change in the momentum of the particle. Okay, so impulse is basically just change of the momentum in the particle. Now there they give us a standard integral which you might need to solve some of the problems, and then an impulse curve. And then here where you were supposed to watch this video and then answer these questions, we will go straight to the numerical questions. Okay, number 2. Okay, the question asks, this is impulse by the way, still on impulse. Number 2, question, numerical question. A car moving at 10 meters per second. So we have a car, its velocity is 10 meters per second. This car crashes into a tree and stops in 0.2 seconds. Okay, so the time, the change in time, okay, is 0.26 seconds. Okay, calculate the force the seat belt exerts on a passenger in the car to bring him to a halt. Okay, the mass of the passenger is 70 kilograms. So the mass of the passenger is 70 kilograms. I wrote down everything that has been given. That is a good way to start a problem. You write down everything that has been given to you, and then you attack the problem. So they want force. Okay, the force of the seat belt exerts on the passenger to bring him to a halt. Okay, now force from the impulse momentum equation, the impulse equation, force is equal to the change in momentum over the change in time. Okay. Now the change in momentum is nothing but mv final minus mv initial over the change in time. Change in time. Let's see. This is going to change in time is 0.26 seconds. The mass is 70 kilograms, which we can take out. We can take the mass out because it's a constant. With the velocity final is 0 meters per second because the car stops after it crashes, minus the initial velocity. Okay, if we take going to the tree as positive, then coming out, then the velocity going backwards is going to be negative. So towards the tree is positive, so this will be 10 meters per second. This will give us negative 10, negative 70. This will give us a negative value. This is going to be negative, let's see, 269. This is what I got, 2692.30. Okay, that is 10 times 70 is 700. 700 divided by point, let's check on decimal. It's going to be 700, negative 700 basically, because that's 10 multiplied by negative 10 multiplied by 70 is negative 700. Let me check my own calculation. Divided by 0.26, that gives you negative 2692.30 newtons of force. Okay, Now negative means this force is acting in the opposite direction of which the car was, which makes sense because the force of the seat belt is pushing you back towards into the seat, towards opposite of the direction of the initial velocity. Okay, the force is pushing you back into the seat. That is the force of the seat belt. So the force of the seat belt is 2692.30 newtons. Okay. Now, number 3. Next question. I'm just checking my notes here. Question number 3 is an A and a B part. Okay, let me just remove this. Question 3 is an A and a B. By the way, the answer is there, 2692.31. We got that. You may need friction. Question number 3. Suppose a child drives a bumper car head-on into the side rail. So the child is driving a bumper car and bumps into the side rail. Okay. Now this side rail exerts a force of 4,000 Newton on the car for 0.2 seconds. Okay. So the side rail exerts a force of 4,000 Newtons on the car for a time period of 0.2 seconds. They are asking what impulse is imparted by this force. Now we know that impulse is equal to F times T. F times T. Now if we take the positive movement of the car is towards the side rail, then every vector against that direction would be negative, and the force is in the opposite direction of the initial velocity. So the force will be negative 4,000 newtons multiplied by the time this force acts on this bumper car. It is 0.2 seconds. So basically 2 divided by 100 times 4,000. If there's 100, it's 42 times 40 is, no, is it 40,000? Wait, let me just check. 4,000, 0.2 seconds, 800. Yes, it is 4,000 newtons. It's for 0.2 seconds. It's 2, no, it's not 2 over 100. Yeah, it is 2 over 100. It's 20 over 100, so it's 800. Just check my math here. It's 20 over 100, so that'll cancel that. So it's 40 times 20, so it's negative 40 times 20, that's 800. Okay, so negative 800 kilograms per meters per second. Okay, because force is in newtons and the time is in seconds, so the impulse will have units of kilograms per meters per second, same as that of momentum. Okay, so that is number A. This is the impulse is imparted by that force, the impulse imparted by the force. That is the impulse imparted by the force acting of the side, the force of the side rail acting on the bumper car. Now The question is find the final, the question B is find the final velocity of the bumper car if its initial velocity was 2.8 meters per second. Okay, we'll do B on the next page. I'm not gonna have space here, so next page are we going to do B on. Okay, so let's see. Find the final velocity of the bumper car. So we have the bumper car B. So we have the impulse. The impulse is equal to negative 800 kilogram per meters per second. And then we also have the initial velocity of 2.8 meters per second. We need to find the final velocity. We need to find the final velocity, and the mass of the car and the kid is 200 kilograms. Okay, so let's see. Impulse is equal to change in momentum. Impulse is equal to the change in momentum. Now the change in momentum is the mass initially, mass final. The momentum final minus the momentum initially. Okay. Now mass is constant, so we can take it out. So it says the velocity final minus velocity initial is equal to impulse. Velocities are vectors. Okay. Now we know that the impulse is equal to negative 800. The mass is 200. The velocity final is what we want. The velocity initial is 2.8 meters per second. First we divide by 200, giving us negative 4. So velocity final minus 2.8 is negative 4 meters per second. Negative 2.8, if we add that, if we take it over, it becomes positive. So velocity final, therefore the velocity final is equal to negative 4 plus 2.8, which is equal to 1.2 meters, negative 1.2 meters per second. Now according to this, the final velocity is negative, and that is going to be okay. Is what we expected, because the force is acting opposite the initial direction of velocity, which was towards the front, towards the side rail. But now this force is acting opposite that direction of the initial velocity, and if the force is acting in this direction, then the acceleration must also be in the direction of the force, and if the acceleration is in this direction, then the final velocity must be in this direction. Okay, that makes sense. Now going on, question number 3. We did question number 3, we're going to question number 4. We'll do number 4 and number 5, and then I want us to look at one problem in the book. Okay, a linear momentum problem in the book. So let's get on with it. Okay, so a 75 kilogram person is riding in a car moving at 20 meters per second when the car runs into a bridge abutment. Okay, calculate the average force on the person if he is stopped by the padded dashboard that compresses an average of 1 centimeter, and then calculate the average force on the person if he is stopped by an airbag that compresses an average of 15 centimeters. Okay, so you are riding in a car. Picture this: you are riding in your 75 kilogram person sitting in your car, and you're moving at 20 meters per second. Okay. Now, when the car hits a bridge abutment, I assume that it's something near the bridge. I don't know exactly what it is, but if I had to guess, I think it's one of the sides at the front of the bridge, near the entrance of a bridge. But I'm speaking under correction. But whatever it is, you hit this thing, a bridge abutment. Now, you need to calculate the force acting on the person if he's stopped by a padded dashboard that compresses an average of 1 centimeter. Okay, so you hit the dashboard, and the dashboard compresses, and you are weighing 75 kilogram. You hit the dashboard, it compresses after you hit it. When you compresses by 1 centimeter. Okay. Now, you have an initial velocity. You want to know what your final velocity is because you traveled a distance of 0.1 centimeters, and you traveled 1 centimeter basically. You have an initial velocity of 20 meters per second. You travel 1 centimeter, and you want to know what its final velocity is after that 1 centimeter of travel. You come to a stop after that 1 centimeter of travel. Like you hit, let's say this is the dashboard. You hit the dashboard, you have a fun, you come to a stop. You started from 20 meters per second, you come to a stop after the dashboard is crumpled by 1 centimeter. First of all, you need to then calculate the acceleration. They said there, calculate the average force. Now we can calculate the force if we have the acceleration. Okay, so the force final squared is equal to the force initial squared plus 2 times the acceleration times the change in distance. Okay, now the final force is you come to a stop, so it's 0. The initial force, or the final speed, the final velocity is 0 because you come to a stop. The initial speed is 20 meters per second. That is also squared, sorry. Plus 2 times the acceleration, which is what we want because we need to calculate force. And the distance you traveled in that time is 0.01. Just make sure, yes, it is 0.01 meters. Okay. Now, if you work that out, you will come to the following answer. Okay, if you work it out, your answer will be that the acceleration is equal to negative 20,000 meters per second squared. Okay, so it's just going to be 0 here. That's going to be 400, negative 400 divided by 0.02. Okay, let's see, negative 400 divided by 0.02. Let's check if my calculations were correct. Negative 400 divided by 0.02 gives us negative 20,000. Okay, there. I can't seem to be able to show you now let me just zoom out for a bit so you can see. Let's see if you can see it now. If I scroll up, it won't scroll up. Okay, never mind that. Okay, so I did it here and it got negative 20,000. I just wrote the answer there. Okay, so the acceleration is negative 20,000. Means it's accelerating at negative 20,000 meters per second squared to get you to stop from 20 meters per second to 0. Okay, now we can also calculate the time then it takes you to stop. Maybe because you have the information to calculate it out, how long it takes you to stop, because you have the acceleration and the initial speed. You have the acceleration and the initial and final speed, so you can calculate the time it takes you to stop. Okay, and if you have the time it takes you to stop, then you can also calculate you have the initial and final velocity, so you can calculate impulse. You can use it to calculate the impulse. Well, the impulse formula also. Okay, so let's see. You have the mass as well, so you can go. The force will then be equal to mass times acceleration. And we have the mass as 75 kilograms. And the acceleration is negative 20,000. So the force is going to be negative 1.5 meganewtons. So it's just going to be negative 1.5 times 10 to the 6 newtons. Okay, that's mega. That's mn, and that is the answer that their book also got. Okay, now that is A. That's question A. B, they ask, for B they ask us to calculate the average force on the person if he is stopped by an airbag that compresses an average of 15 centimeters. Okay, so the average force of an airbag, the average force on the person if he is stopped by an airbag. So this is the force if he is stopped by the dashboard, 1.5 newtons. And if he's stopped by the airbag, let's see how much force is on him. Same scenario. The initial plus 2 acceleration times the change in distance. Now, let's see. Final velocity is still 0, initial velocity is still 20, plus 2 times we need the acceleration. The changing distance is now 15 centimeters. So 15, so 0.15 meters. So the airbag is compressed more than the dashboard. So therefore the acceleration is then equal to negative 13, negative 1,333 meters per second squared, which is much less than that negative 20,000, which means it's slowing down faster, which means if the acceleration is less, the force will be less. And if we work it out, we see that F is equal to ma. The force is equal to 75 kilograms multiplied by the acceleration of negative 1333 meters per second squared, and the answer will then be negative 0.1 times 10 to the 6 newtons, or just negative 0.01 meganewtons. Okay, this means that this force is significantly less than that one. Okay, it is significantly less, which means the airbag is going to do a lot less damage than the dashboard. Because number one, the airbag is compressed further than the dashboard. That is why in car crashes, this is now for impulse, in car crashes, okay, force is, let's say, impulse, the change in momentum. Okay? Impulse is equal to the change in momentum. This is just for some notes how my old professor explained it, which is equal to force times time. Okay. Now force is then equal to the change in momentum over the change in time, correct? Then you explain this way: the smaller this force, the smaller this time, the larger this force acting on you will be on you in a car crash. Okay, so if you can somehow increase this time, then the force acting on you during a crash will be much smaller. That is why most modern cars has a bumper or front part that crumples during the accident, okay, or the collision. The reason for that is that crumpling extends the time of the collision, okay, which means the force acting on the person will be less than it should have been if it was just a rigid crash. Okay, a rigid crash without any crumpling would take very fast, so it'll be bam, it's over. Okay, it takes a lot less time that way, but the force, according to this, the change in momentum will be the same, but the force will be much higher if the time of collision is much smaller. If the time of collision is smaller, the force will be higher. So car manufacturers have developed cars that crumple during collisions to increase this time of collision, because if you increase the time of collision, then the force acting on your passengers or your will then be much lower, and then that will in turn have saved lives. Okay, let's go to our last question for collisions in this book, for momentum. Let's see now. I'm going to do this one, and then we're going to do one more from the book. But before I do the one from the book, I'm just going to go drink some water because my throat is really getting dry now. So here we go, question number 5. Calculate the final speed of a 110 kilogram rugby player. Okay, so the mass is 110 kilogram. He's initially running at a speed of 8 meters per second. And he collides head-on with a padded goalpost and experiences a backward force. So the force is negative 1.76 times 10 to the 4 newtons. And that force acts over a time period of 5.50 times 10 to the negative 2 seconds. That's 0.05 seconds. They want us to calculate the final speed of this player. Now, let's first calculate the change in momentum. The change in momentum, or the impulse, is equal to force times time. That is force acts. Now the force in this case is negative 0.176 times 10 to the 4 newtons, acting on a time period of 5.5 times 10 to the negative 2 seconds. Okay, if you work that out, you do the calculations. First, let's calculate the impulse, or in other words, the change in momentum is also the impulse. It's the same thing as the impulse. So we first calculate the change in momentum, or the impulse, and it's just going to be the product of the force times the time. The product of the force and the time. Okay, so the force is 1.76 times 10 to the 4 newtons, multiplied by the time it acts, so it's 5.5 times 10 to the negative 2 seconds, and that gives you negative 968 kilogram meters per second. So that is your change in momentum. We also know that the change in momentum is equal to the momentum at the beginning, which is mass times velocity final. Mass times velocity final, the momentum at the end minus the momentum at the beginning, mass times velocity initial. Now we can take the mass out. It'll just be velocity final minus velocity initial. Okay. Now the mass, we know that the change in momentum, which we already have as the dp, we know that mass, the momentum final minus the momentum initial, is going to be the change in momentum. We can take the mass out because mass is constant in this case. In rockets it doesn't work that way, the mass changes because it's burning up its fuel. Now let's see. The mass is 110 kilograms. The velocity final is what we want. The velocity initial is 8. Meters per second. The impulse is negative 968 kilograms meters per second. Okay, therefore, if you work it out, you divide by 110 and you add 8, you get, or I at least got a velocity of negative 0.8 meters per second. Which makes sense because once he smashes into the rigid goalpost, the post is not moving and he's effectively came to a stop and he's just moving backwards slowly. Okay? And that is all that we have for momentum, but there is one more problem that I want to do on momentum, then we'll go to movement of a rigid body. Okay? But the problem I want to do is in Serwin-Chewit. I will give it to you for now. This problem here. It is a problem where momentum is in terms of unit vectors. We have done so far, up to this point, we've done them all in one direction. But in this case, I want us to do one where the momentum is in unit vectors, okay? So, let me just, for a moment, I want to check something. Okay, so the thing is not responding now, but while it responds, I'm just gonna go drink some water. Okay, so just digest that problem for a bit. I will come back now, we'll do it, and then we'll be done with momentum. We'll go to rigid bodies. Hi everyone, I'm back. Let me just get pointed here. Problem is there. Okay, so the problem says a 3 kilogram particle. Let me just move it this way. A 3 kilogram particle. Let me just check if the YouTube is still running. It seems to be still running. Okay, good. Okay, a 3 kilogram particle has a velocity of, and this particle is moving in both the x and y direction because it has a I hat and a k hat component. Okay, so a 3 kilogram particle has a velocity of 3 I hat minus 4 j hat meters per second. Okay. So this is number 3, and this particle has a velocity of 3 I hat and negative 4 j hat, okay, in meters per second, of course. Okay. Only deal with meters per second in this course. Now it says A, find its x and y components of momentum. Okay, so find its x and y components of momentum. Okay. Now the vector momentum is then the vector momentum is then momentum is equal to mass times velocity. Okay, we get that mass times velocity is the momentum. Now the mass is equal to 3 kilogram. The velocity is equal to 3 I hat minus 4 j hat. So there we have the mass. Okay, I'm just switching from screens here so I can see what I'm doing. Okay, I'm just checking if there's any questions or if any views yet, or if any of you can have any problems. Okay, or even if the video is still streaming. Okay, now getting back to the problem at hand, and that is in meters per second, of course. Now multiplying that all out, we get 3 multiplied by 3, we get 9 in the I hat direction, so 9 kilogram meters per second in the I hat direction, minus 3 times 4 is 12 in the j hat direction, and that is in units of kilogram meters per second. There we have the momentum. So thus the momentum in the x direction, the x component of momentum, is going to be 9 kilogram meters per second. The momentum in the y direction is negative 12 kilogram meters per second. That is basically, that is the x component of momentum, that is the y component of the momentum. Now they're asking us for B. They're asking find the magnitude and direction of the momentum, so the net momentum, so the magnitude. Now we know how to find the net vector. Okay, so momentum is a vector, and how we find the net of a vector which has a horizontal and a vertical component? We take the horizontal component, square it, take the vertical component, square it, and we find the square root of that answer. That will give you the magnitude of this vector. Okay, and in this case it's going to be 9 kilogram meters per second squared plus negative 12 kilogram meters per second squared. That will give you 81 plus 144 is 69, isn't it? 169, or 220, I can't remember. No, that is not those. Can't remember my special triangle. Kilogram meters per second, that is the net momentum of this particle. It is net momentum. Of course, you can also work out its direction then, given that you have its so that, ladies and gentlemen, is on momentum. We will end there for momentum. Now let's go to motion along the axis, along around. Let's go. See, I'm just going to go some. This, by the way, is a very, very good textbook. I remember that the parallel axis theorems, and I did it in my second year. Very, what can I say, not for the faint-hearted. Now, here, what I want us to look at. When a rigid object rotates about a fixed axis, meaning, say, a car wheel, the angular position, angular speed, and the angular acceleration are related to the translational position, the translational speed, and the translational acceleration. Okay? By those formulas there, the angular position is just the radius multiplied by the angular translation. Why? I'm just checking something here. They're using S, V, and I for the angular position to the translational position, the translational speed, and the translational. It's kind of weird because, but let's leave it at that. But this is not what I want to discuss. This is okay. Angular position definitions. We're not at torque yet. You're not doing torque yet. You're just doing angular position of a rigid body is defined as the angle theta between a reference line attached to the object and a reference line fixed in space. And you also have angular position, but I want to get to, I don't see it here, the angular, not the angular, the equations of motion in terms for rigid bodies. There's the parallel axis theorem, moments of inertia, that's torque. Here, these equations are the ones I'm looking for. These equations. A rigid body under the kinematic equation for rotational and translational motion. Okay, this is translational motion, and of course these are the rotational motion, okay, under constant acceleration, of course, must be constant acceleration. Okay, let's see. Here, these equations you should know very well. You already know the ones on the right, the ones on the left are new. Well, not new, they're the same, they're just for rotating bodies. Okay, rotational translation. Not rotational translation, rotational motion. Okay, it says the angular speed, the final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. Then the final angular distance is equal to, or the angular distance, yes, is equal to the angular speed initially times time plus half of the angular acceleration times the time squared. The angular velocity final times the squared is equal to the angular velocity initially squared plus 2 times the angular acceleration times the change in angular displacement. Okay, those are the equations that you will need in some of the questions that you did in Moodle, but I will not get. Let's get to there are some problems that I want us to look at. There they are. Those are the problems if the acceleration is constant. Rotational motion, useful equations, those equations there. Translational motion. Okay, so those are the for rotation. Okay, you can even get the work from torque. Okay, so you have the final velocity. There's all of those equations that I just mentioned. Those three are very important, and we will be doing problems regarding those three. We will not be doing rods and stuff like that for now. We'll be doing all of these problems that I picked out. This is the first one, problem number 2. Potter's wheel. Problem number 3. And problem number 4. I think you have done problem number 4 with one of the other tutors, I can't remember who, but I will do it again nonetheless. Problem number 5. Problem number 11. And that will be it. Let me just check. Yes. And 13. Those are the problems that we'll be doing today. Just want to get you well equipped with the equations of motion. do a whole bunch of problems. They say if you want to be well in physics, you got to do examples, examples, examples. Okay, so rigid body problems. Let's see. Question number 2. This is the I'm just checking what is the name of this topic. Where is it now? I'm moving, I'm looking. Okay. Rotation of a rigid body. Rotation of a rigid body about a fixed axis or around a fixed axis. Rotation of a rigid body about a fixed axis. This is in Survey and Jewett. We'll be doing problems from Survey and Jewett. Chapter 10, is it? Chapter 10. From the 9th edition. But you don't have to go consult the book. You can consult the book for other problems, yes, but I will be showing you the actual problems here on the board, and there they are. Okay, and my head is just covering it now. Okay, I'm wondering if I could move myself here. Where is the fact that I can move? I just want to move it upwards. I just switched myself off for a second so we can see the problem there. Problem number 2. The problem says, a potter's wheel moves uniformly from rest. Okay, so it moves uniformly from rest. Just uniformly from rest to an angular speed of 1 revolution per second in 3 seconds. Okay, so it moves uniformly from rest to an angular speed of 1 revolution per second in 30 seconds. Okay, the first question is A, find its average angular acceleration in radians per second. Okay, so angular acceleration is equal to angular velocity is equal to the change in angular acceleration. Sorry, the wrong formula. Angular acceleration is equal to the change in angular velocity over change in time. Now, the speed is in 1, the final speed is 1 revolution per second, and it starts from rest, so its initial speed is 0 revolutions per second. So our answer is going to be in revolutions per second, and the time it takes to reach that is 30 seconds. So our angular acceleration alpha is equal to 1 divided by 30, which is 3.33 times 10 to the negative 2 revolutions per second squared. Now we want the answer in, they ask us find its average angular acceleration in radians per second. Okay, now there are 2 pi radians, 2 pi radians in 1 revolution. Okay, so 1 complete circle is 2 pi radians. So there is 2 pi radians in 1 revolution. Revolutions cancel out, which leaves us 2 pi times that answer. So it's 6 times that. I'm going to hazard a guess and say around 1820, which gives us, moves it 2.209 radians per second squared, and that is the angular acceleration of this body, this potter's wheel. Then D asks the question, would doubling the angular acceleration during the given period have doubled the final angular speed? So let's say they say if we doubled the angular acceleration, so if we double the angular acceleration but we kept the time the same, with the final angular speed have doubled? Yes, because this should have been, would be then be have to be double the original if we want to double the angular acceleration, average angular acceleration. Yes, the answer is yes. Now the reason is when the object starts from rest, its angular speed is related to the angular acceleration and time by this equation. Okay, so you can just use that equation to explain what is happening. Now, number 5. Another good question. No, this number 3. Sorry, good question. Number 3. Okay, it says during a certain time interval, the angular position of a swinging door. Okay, so a door is swinging. Okay, it is moving about its axis, which is, let's say this. Let's look at this. Let's say this is a door from above. We're looking at it from above. It is swinging in a direction like that. This is the door. That right there is the hinges, which means it is moving in a quarter circle or a semicircle, a door. Depends on the type of door. Now it says during a certain time interval, the angular position of a swinging door, this door is swinging, is described by theta. So the angular position of this door is equal to theta. Theta is equal to, is described by this formula, 5 plus 10t plus 2t squared. This is the formula describing the angular position of this door. Okay, where theta is in radians and the time is in seconds. Okay, t is all usually measured in seconds. Now it says here, determine the angular position, angular speed, and angular acceleration of the door. Okay, so determine the angular position, angular speed, and angular acceleration of the door at t equals to 0 and t equals to 3 seconds. Okay, so the angular position is equal to, this is a problem that you had sometimes. Some of you guys had, the reason why I picked this one is because sometimes you guys had problems with this in translational, in just classical translational. I can switch this on now. Okay. Sometimes you guys had problems using this in translational mechanics. Okay, so here, let me just remove that. We need to determine the angular speed, the angular acceleration, plus 10 t plus 2t squared. So we need to determine the angular acceleration, the angular speed, the angular position at t0, t. Okay, so this is the angular position. We are given the angular position. Okay, now the angular, this is A. Let's first calculate all the formulas, and then we can calculate them for those seconds. Okay, for a t equal to 0, you can just plug that in, but I just want you, the reason why I picked this problem, you can plug, we won't be plugging it in, or we can if we want, but the angular, this is the angular acceleration. This is the angular position. Now the formula for the angular, let's get the formula for the angular speed. The angular speed is equal to dw dt, which means it's just going to be the time derivative of dw d theta, sorry, the time derivative of 500 plus 10 t plus 20t squared. Okay, that is going to give us 0, 10 plus 2, that is going to come down, that's 400t. Okay, so there we have a formula for the angular speed, we have a formula for the angular position, a formula for the angular speed. Now for the angular acceleration, the angular acceleration is dw over time, which is nothing but d dt from calculus of 10 plus 40t. That is going to be 0, that is going to be 4. So the angular acceleration is constant at 4. Okay, the angular acceleration is just 4 rads per second squared. Okay, now you have a formula for the angular position, a formula for the angular velocity, and a formula for the angular acceleration. Okay, now you can just plug in 0 and 3 everywhere you see a t, and that will be your answers. Okay, the acceleration is at 0 seconds will be 4 rads per second, and at 3 seconds it will be 4 radians per second. The angular position, the angular velocity will be, if you plug in 0, you get 10 radians per second, and then if you plug in 3, you will get 12, that's 22 radians per second. The position will be 53 if you plug in 2 there, and then 3 in there, and then 0 if you 5 if you plug in 0. Okay, so you can plug that in there. I will leave that up to you guys. Okay, so yeah, I don't know if you guys saw that, but the angular acceleration is just dw dt equal to d dt of the angular velocity, and it's 4 radians per second. The plugging in is not what's important. What is important is the fact that you know how to do that. Okay, I continue with question number 4. Okay, so should we do number 4? No, that involves some calculus, so let's rather skip number 4. I wanted to do it, but it's a little slightly high level, but it's just some calculus. It's not that difficult, it's just some calculus. I want to first get us acquainted with these questions. Okay, so we'll go to number 5. Question: a wheel starts from rest. So we won't do number 4, we'll do number 5. A wheel starts from rest and rotates with a constant angular acceleration to reach an angular speed of 12 radians per second in 3 seconds. Find A, the magnitude of the angular acceleration, I assume, the angular acceleration of the wheel, and then b, the angle in radians through which it rotates in this time interval. Okay, so first let's find the angular acceleration. Okay, angular acceleration is equal to the change in angular velocity over a change in time. Now, its angular, it changes from, starts from rest, so its initial is its initial is 0 radians per second, and its final is 12. Angular velocity is 12 rads per second, and it goes from 0 to 12 in a time frame of 3 seconds. So 12 divided by 3 is 4 radians per second per second. So this is the angular acceleration of this wheel. Okay, the angular acceleration of that wheel is 4 radians per second. Okay. Now the angle in radians through which it rotates is then equal to the angle in radians. That is for A, this is B. The angle in radians through which it rotates, alpha, is equal to, we've already gotten the angular acceleration, alpha is equal to 4 radians per second per second. Now we want the angular position through after 3 seconds. Okay, so want it in radians. This is the formula you will use to get angular position. So half angular acceleration times squared. Okay, so the initial velocity is 0. The initial angular velocity is 0 multiplied by the time, which is 3, plus a half times the angular acceleration is 4 times the time is 3 seconds squared. So it is 3 squared is 9 times 4 is 18. 18 is 36. Half of 36 is 18. 2 times 9 is 18. So 18 radians is how far this wheel travels. So 18 radians is how far this wheel travels in 3 seconds. Okay. Now let's go to the next problem. A rotating wheel. These are the last 2 problems that we'll do. Then we'll call it a day. Now note, we did start earlier today, a lot earlier. So we'll go to problem number 11. Problem number 11 involves 2 unknowns. It's basically the same problem, but you have to solve one, get the other, so let's leave that. Problem 13. Why did I pick problem 13? Oh yeah, it's because it's the same as the one there, but you seem to be familiar with these problems now. There is one problem. Okay. This is the problem. It's in your TED. Okay. I think we've done quite a lot. I think we can call it a day now. Okay, we did start a whole lot earlier, so I'm going to say goodbye now, guys. Have a good weekend. to any of the any viewers, I'm going to say bye now. I did start an hour earlier. Then we did a lot of extra problems. So enjoy your weekend and